All right, today's lesson is about current and voltage, or voltage and current. And the last lesson that we had, we used the analogy of hockey to start getting into some of the basic concepts around electricity and circuits. We're going to use that same type of idea, except we're going to make a few changes to it. We're going to keep this idea, though, that the puck represents electric charge. And that electric charge, we now know, is being made up of these things called electrons. The thing is though, is that it's not just enough to have electric charge. If we're talking about current electricity, we are talking about moving electrical charges. So it's this puck being in motion, which is what we saw last day in our hockey analogy. The thing we're going to change, though, is what is causing this thing to move. Now, in the last lesson, we had, hockey sticks and people shooting the puck and stuff like that, and that was representing this becoming a moving object or a moving charge, and that is what created current electricity. We're going to find out that there's other ways of making a puck move, and we're going to keep it really simple for this analogy. We're going to do it as a simple drop. And in case you're wondering, hockey puck, collector's edition, Vancouver Canucks, 84-85. Good times. So simply dropping the puck causes the puck to move, and this is a moving charge, so as a result we can consider this to be current electricity. Now we can measure the rate at which these charges pass a certain point using something called amps or amperes. It's basically how we measure current electricity or current. And you would measure current using something called an ammeter, or in this case, a multimeter with an ammeter function. Okay, so great. So we can get a charge to move, creates current electricity. We can measure that using something called amps or amperes. Why is that so important? Well, like we said before, this is a form of energy, electrical energy, and energy is the ability to do work. So the thing is that these charges, these moving charges, this energy can be used or converted or changed into another form of energy, and that energy is what we can then consider as being the work that we want to do. For example, I can take this electrical energy and I can convert it to mechanical energy or kinetic energy. If this dropping charge or this dropping puck, this moving charge, is used to literally spin a fan or a motor, that motor is then taking the electrical energy and converting it into kinetic energy or motion or movement. This electrical energy can be converted into heat energy if it's used to heat up a heating element on a stove. This electrical energy can also be used to, say, power a light bulb and convert it from electrical energy into light energy. So that's the reason why moving charges or current is useful to us, is because this electrical energy can be converted into other forms of energy and the ability to do work. So on your Chromebook, and according to the sticker on the back, it requires an input current or an input amperage of about 2 to 3 amps of current. This typical household LED light bulb draws in about 0.5 amps of current. Now, you'll also notice that I'm dropping it from a certain height and it's going a certain distance before I catch it in my hand down here. But this height between here and where I'm catching it in my hand, we can consider that to be voltage. It's this potential energy. It's this energy that is potential in this charge. By the time I release it and it hits my hand down here, it has now a certain amount of energy as a result of how far it's fallen. This is this potential energy that I'm talking about. And when we're talking about it for electrical circuits, this potential energy is called voltage. And we would measure voltage using something called volts. Now, I know there are different ways of looking at voltage. Some places might describe voltage as the push behind these charges or these packets of electrons. Others might say it's this pulling force. Whatever it is, it's just a way of describing what is the actual thing that is causing these electrons to move. There is this desire for this puck to move. As soon as I release it, it wants to move. And that's the potential energy that we're talking about here. That's the voltage. And you'd measure voltage using a voltmeter, or in this case, with my multimeter, turning it to the voltmeter function. So the question is well, can we change the voltage or the value of voltage? And what does that mean, or what does that do? So if we're again saying that the height or the distance that I'm dropping it represents the voltage. Using this puck analogy, if I were to increase the voltage, it'd be like me while increasing the actual height at which I'm dropping the puck. And if I were to say drop it, let's say instead of from here to here, I were to go from the height of the ceiling and dropping it down to the floor, that would be me increasing the voltage. If by holding this up higher and increasing the voltage, we would notice that by the time this puck hit the ground, it would be moving at a faster speed than if it was held closer to the ground. This is the impact that a higher voltage would have on current flow. It would increase current flow. So if we were to increase the voltage, we would also increase current. And don't forget, that increase in current that we're experiencing because we've increased the voltage, well, that increase in current, that electrical energy that we get can be used to do more work. Here is a AA battery, and this supplies 1.5 volts. 2 terminals, one up top here and one at the bottom there. You typically use this for small electronics in remotes. I'll use them for stuff like if you have a wireless mouse, you'd use 1 or 2 of these in that. So this is a AA 1.5 volt battery. This is what we call a 9 volt battery, and the 2 terminals you can see are at the top here and there. And you'd use this type of battery for slightly larger electronics, or I use them actually mostly for stuff like smoke detectors, carbon monoxide detectors and stuff like that, garage door openers. You'd see batteries like this, the 9 volt battery. So moving away from batteries, this is an outlet, typical household outlet. Now, obviously, it's not wired up, so it's not live. But if it was, the terminals that you'd be using would be these 2 here or these 2 over here like that. And these would supply 120 volts, a fairly common way that we can bring power to many of our devices at home. So these types of outlets, you're going to see behind, like if you have a clothes dryer at home, or if you have an oven, electric oven, you're going to see one that has a plug like this. These will send out 220 to 240 volts of electric potential. So you can see the types of devices that would make use of something like this. These are often much larger and much more power hungry type of devices like ovens, clothes dryers, and stuff like that. Now I'm going to throw this one in here because of our experience with static electricity, and we have spoken about static electricity. But if you've ever generated enough static charge, let's say if you've got socks on and you can sort of scrub your feet along a carpet and generate a static charge and actually shock somebody, that kind of voltage that we're talking about there, and especially those kinds of shocks where you can actually see like the light jumping between your finger and your victim, you could be looking at voltages of about thousands of volts, 20,000 volts, 30,000 volts for that electric shock. And some of the largest voltages that you're going to see are in thunderstorms, lightning, and those types of voltages. You're looking at voltages in the millions. All right, so that's the end of our little hockey analogy. Let's go back to actual circuits and let's see how this actually applies, current and voltage. All right, so I have my simple circuit set up here. You can see I've got my battery set up there, and I've got my complete circuit. There are no breaks. I have a load in here, the light bulb, and you can see that we've got the charges moving through here. Now we know that these charges are basically electrons, but they are moving, and as a result we call this current electricity. Now the reason why they're moving is because we have this battery here providing this push or pull of these charges, because it's providing this potential energy known as voltage into the circuit, and as a result these charges are moving through this complete path. We can measure this. In fact, we would measure the voltage or this electric potential across this battery using a voltmeter, and you can see I've got a voltage here of 9 volts. And we can also measure this current in the wire by taking an ammeter and measuring the current, and you can see I've got a current of 0.9 amps. Let's increase the voltage. So we can click on the battery, and you can see we've got the slider here. So I'm going to slide this up to, let's say, 90 volts, which is not necessarily a great voltage for a battery, but here it is. And you can immediately see as soon as we increase the voltage, the current flow also increases. You can see these charges now flying through here. And because we have more of this electrical energy, this light bulb actually has the ability to become brighter. It can do more work for us. So this is the result of this increase in voltage. Now we can measure this. We can take the voltmeter again and attach it there and measure the voltage across this battery. You can see it's got a voltage of 90 volts, just like we set it. And we can put here the ammeter, and you can see that the current has also jumped up to 9 amps. So there it is. Increase in voltage results in an increase in the current flow. There's something else that we need to talk about when it comes to current flow, because there are two different ways of describing current flow. It's the movement of charges in a circuit. You can kind of see in our example here, you can see the charges moving through the circuit. Now, currently we have a good understanding about what those charges are made up of. We now know that it's made up of electrons, and we know that electrons have this negative charge to them. So if we start having a positive and negative end of a battery, or having a positive and negative terminals in an outlet, we would know that the negative charges would want to flow from the negative terminal and get attracted to the positive terminal. That's really the flow of these electrical charges that we now know of as being made up of electrons. But way back when, we didn't know much about the atom, and as a result, when we started looking at electricity, they sort of assumed that the charges were positive, and they would describe the charges in a circuit going from the positive terminal to the negative terminal. We now know that is not necessarily correct. So as a result, we have two ways of looking at current flow. The first way is the old way, which is the flow of these charges, which we thought of as being positive, from the positive terminal to the negative terminal of a circuit or of a power source. And that is called conventional current. So if you hear the word conventional current, you will see that it's this thought that the charges move from the positive terminal of a power source all around the circuit to the negative terminal. But in reality, we know that the actual charges made up of electrons are moving in the actual opposite direction. It's moving from the negative terminal or the negative terminal of a battery or power source around the circuit to the positive terminal. Now, thankfully, in terms of how we design circuits and stuff like that, it really doesn't change too much. It still works. It's just that you now have these two different terms of describing current flow. And I don't want you getting confused about it, because you might see some diagrams that will show the arrows going from the positive to the negative terminal. You just have to understand that they're describing there the flow of current as conventional current. You might see other diagrams that will show arrows going in the exact opposite direction, and what that's showing you is they're understanding that it's the electron flow that is going from the negative terminal back to the positive terminal. Sorry. All right, so that's it. That's the end of the lesson. Next is going to be what I want you to work on today. It's, again, getting you to play around with building circuits, but now applying these concepts of current and voltage, and for you to understand how those values change in a circuit when we start arranging batteries or loads, in this case light bulbs, in different arrangements, and then you using an ammeter and a voltmeter to measure those values. Pretty straightforward, but we are building up towards something, so just bear with me, and hopefully this all makes sense. And it's just to deal with how to work these two meters. And the one here that measures current we would call an ammeter, and this one here that measures voltage is a voltmeter. And I just want to sort of make sure you understand how to use these things when it comes to the simulator. And they are very similar in how you would attach these in real life if you were to use an ammeter and a voltmeter. But you can see here I've got some batteries in a row, 3 batteries in a row, and I've got 2 light bulbs or 2 loads in a row there. Measuring current's really simple. Basically, you are just measuring the amount of current flow past a point, and so as a result, they have you, for this simulator anyway, just sort of dragging this sort of scope, I don't know what you call that, on top of any section of wire or any part of the circuit, and it would read how much current is flowing through that particular point. And again, don't forget it's measured in amps. The one I want to really make sure you understand is this, the voltmeter. When it comes to the voltmeter, you'll need to sort of attach these two sort of ends here, and you're going to measure voltage across
certain parts of a circuit. So right now, the way I have these two leads arranged is I'm measuring the voltage across both of these light bulbs. And that's why I have one lead over here and then two light bulbs and the other lead on this side. That's what I mean when you're measuring voltage across either a load or a group of loads. So if I wanted to measure the voltage across just this light bulb, I would have to move this one over here and then take the voltage reading there. Now, the other thing that you might notice is, and I'll see if I can illustrate it over here. I'll drag this voltmeter over here. I can do the same thing with batteries. I can measure the voltage across one battery like so, and that should give me some sort of reading there. There it is, 9 volts. If you ever come up with a voltage, and I'm going to purposely do this, and you have these leads and you get a reading that is not minus a negative reading, that just means you have your leads sort of crossed. Now in here it sort of works out that it works just like that, but you might have another part of the circuit that you're measuring, or the way you build your circuit, and you attach the leads to measure the voltage across either a battery, group of batteries, or some loads. And if you get a negative reading, that means you just have your leads sort of flip-flopped and you just got to exchange the leads, or if you just want, just take away the minus sign, and that's the voltage reading there. All right, I just wanted to make sure that we were okay with that, because when you complete this next sort of activity, you're going to make use of both these meters, and I'm going to ask you to measure the current in certain parts of a circuit, or to measure voltage across either one load, two loads, maybe three, or 1, 2, or 3 different batteries. And I just want to make sure you understand what I mean when I ask you to do that. All right, so there it is. Good luck with the assignment, and I'll see you guys later.